Hi, we're looking at the ring light project once again today, and primarily we're going to take a look at the layout. Now, I have made some changes to the schematic based on the feedback on the last video, so I do really appreciate that feedback. It's guided a few of the changes, and we'll take a look at that in a moment. Now, also since the last video, I have ordered some of the parts from Mouser, primarily just to secure the stock, because I didn't want the LEDs in particular suddenly going out of stock and then being left without the LEDs that I'd primarily chosen. But if we have a look, I did actually make a slight change. This time I've gone for the XHP50B, and this is the slightly newer version of these XHP50 LEDs. And these are slightly more efficient, but the main thing that I noticed is these are actually cheaper. So I ordered 12, so at that price you're getting them at £3.54 each. So we're spending about £20 including VAT on the LEDs, which isn't too bad at all. And these are very slightly brighter. Now, the ones that I actually got were the 5000 Kelvin COI of 90, but I wasn't able to find the H4 binned devices. So these ones are very slightly dimmer, but I'm not too concerned about that too much. The other thing that I found quite interesting is somewhere in the datasheet, I can't remember where it says, but the colour temperature and the COI is actually specified at 80 degrees C. So these are expected to get quite hot. So the heat sinking might not be too bad for the types of currents that we're looking at. I have ordered some heat sinks as well. They're fairly small. If we have a look, they're about 25 by 28 millimeters, and we'll see how we get on with these. It may be that I make a case for this from some 3D printed material and then force some airflow over these heat sinks, but we'll have to do some testing and see how that behaves. So here is the updated schematic, and here is the updated power section. So first of all, we've got a 2.5mm barrel jack so that we can plug in a standard power supply into this. That goes through to the Schottky diode for reverse polarity protection, and then into the 470 microfarad electrolytic capacitor. Now I've added a power switch, and this is one of these slide switches. This one's from LCSC, and you can see it's a 3-terminal device. And that should be suitable for the power levels that we're talking about. But I've put the switch after the capacitor mainly so that we don't see quite so much inrush current, which ultimately will reduce the lifetime of this switch, and it will either end up like welding the switch contact closed, or it just simply won't work anymore. So that's the reason why the switch is after the capacitor, and then I've just added a little power LED, although the light should come on as soon as the power is switched on. Next up, we've got the brightness control, and I have eliminated the LM78L05. Now, the reason being, a few people pointed out, in the datasheet, these 78L05s do mention that although the input voltage is suitable up to 30 volts, the recommended operating conditions are only up to 20 volts. Now, I'm not really sure of the reason why. Obviously, with high loads, you don't want to be dissipating that much power. I suspect it will be fine all the way up to 30, but what I've done, just to err on the side of caution, is to drop back to a simple Zener diode circuit, because we don't need a particularly tightly regulated rail here anyway. So what we've got is a 2.2k resistor, which is limiting the current into this entire circuit here. And you can see here, we should see a peak current through R7 of 8.59 milliamps. The Zener diode that I've selected here needs a minimum of around 5 milliamps to stay fully in regulation, so we're losing 5 milliamps through there. That leaves us with about 3.59 milliamps for the rest of our electronics. Now, the other thing that someone mentioned is, why don't we use a TL431 voltage reference, and then we don't have to worry quite so much about the precision of some of these resistors. And that's quite a good point, and it doesn't mean any changes really to this. I could eliminate this TL431, which is effectively operating like a Zener diode, but I've adjusted the resistor values up here, and what that means is this reference will clamp at 2.5 volts when a certain amount of current is going through this TL431. And the datasheet suggests for proper regulation to 2.5 volts, if you get about a milliamp through here, it should be pretty stable. So we have selected a couple of resistors here so that at least 1.87 milliamps is going through this entire node. We need 1 milliamp through here, and through the selection of resistors that we've got along here, will be dropping about 250 microamps. So we should have plenty here to keep this node at 2.5 volts. You'll also see that I've got two potentiometers. Now that's not for any electrical reason. I've left the two on here, wired completely in parallel, so that we can have a play with the footprints and also choose two different types of potentiometers. So this one on the left is the more traditional, quite chunky potentiometer, and then this one is quite a small Alps potentiometer. So we can have a look at how that works on the layout. It may simply be that I delete one of these and just go with the bigger potentiometer, because it was mentioned that that does get tweaked quite a lot, and yes, it should be a little bit more mechanically robust than potentially one of these little PCB mounted ones. Then that's going in to the op-amp as it was before, and then potentially filtered by these two components, although I may end up not fitting C6. Now the reason for the op-amp is because with a potential divider like this, if we've got an impedance hanging off the output here, that will affect the voltage that we see on this node. And if we have a look at the datasheet, it does say that the input pin resistance is about 50 kilo ohms, and we've got two of those in parallel, so 25k, and we know that our resistance of this potentiometer is 10k, so we're going to see a non-linear effect on the output here, and we won't get the dimming that we would expect. So by buffering the voltage, then we don't experience any of that, and it should behave exactly as we expect. So because the input to the op-amp here is high impedance, this will literally just wipe between 0.48 volts and 2.5 volts linearly, and we should get very predictable behavior. On the LED drivers, I've just made a few trivial changes. Now, previously I did have some 10 microfarad capacitors here. The only ones that I could find on LCSC for assembly at JLC PCB were 25 volt rated, and with a 24 volt supply going in, that's pretty close, and we wouldn't ever see that 10 microfarad at that bias voltage anyway. I did do a video on this quite a long time ago, I'll link it above, but basically by selecting these 2.2 microfarad capacitors, which are actually rated at 50 volts, we should see a lot more capacitance here than we would have done with a single 10 microfarad capacitor anyway. And similarly, I've added some on the outputs here, and then we've got the connectors for two LEDs on each driver. So that's the extent of the changes on here. I did also update another schematic here with the actual LEDs, and there's not much going on here. So basically one LED on each board, one capacitor, and then a connector of some kind onto the main board. There's also a little tab here for the heatsink. That's just so that there's a net with that name heatsink so that we can add in the thermal vias. That's just a quirk of how Proteus works. So we should be able to take this through to layout, should be able to click on this button, it will do a quick check, and then it should bring up the PCB Layout tool. So the tool's loaded up and we've got all of the components that we're going to be placing on the left hand side here. And then I've also prepared the outline of the previous PCB because it's about as big as we want to go. We can extend a little bit, but probably not much more than about 10mm each side before we start getting in the way of parts on the microscope. We're not going to be having the LEDs on this board, they're going to be on daughter boards as I discussed last time. So this is really the maximum space envelope for all of the components for the driver. Now hopefully we'll be nowhere near this and we'll be able to shrink the PCB down ideally. And I'm going to keep the mounting hole in the middle. That did work quite nicely, but we will need to add some manufacturing notes this time to make sure that JLC PCB actually router that section out. So the next thing that we want to do is actually start laying out those two DC to DC converters, because those are the most critical parts of the design. Now, very kindly, they actually put a recommended layout in the datasheet, although this datasheet, generally speaking, isn't very good. It does hint at what the best layout is, and the idea is that we're keeping the current loops as small as possible. The main problem here is that the LEDs are going to be remote from the DC to DC converter. In fact, they're going to be on separate quadrants because we're going to be driving two LEDs with each driver. So we're going to end up with a little bit of a loop, but by having some output capacitance on this, we've got those three 2.2 microfarad capacitors. That should reduce the ripple and we shouldn't see quite so much noise going around the board. By keeping all of these switching elements, so the diode, the actual switch inside the DC to DC converter, and the inductor all very close together, that should reduce the current loops as far as possible and give us the best chance of getting decent EMC performance. So let's start laying out the PCB, and we want to keep all of that layout in mind. So first of all, we're going to lay out RG1 and all of the components around here. Now we don't need to start anywhere inside the actual PCB envelope, we just want to start laying these parts out. So we've got our tiny regulator here, then it's saying R1, which is R1 actually in our diagram here, should be going across between those two pins. So here is the general essence of the layout. We may need to tweak the components just slightly and also ignore the thicknesses of, for example, the ground connection here. We will have power planes on this PCB, so once we do the ground flood, that all gets taken care of. So we just need to check that over once that's done. So these are just here for now for connectivity purposes, and then our outputs to the LEDs are basically across these capacitors down here. So I need to duplicate this one more time for the other driver, and then we'll have a look at the brightness controller. So we've now got both of the DC to DC converters drawn up, and we need to think about where we're going to place these on the board. Now I've modified the diagram slightly to show a little bit more how this might look. There's going to be an LED in each corner. That's going to be on a separate board, and then the connections to this main board are going to be somewhere at the bottom here on each PCB. We've got the hole for the microscope lens to poke through, and then that flange that I made took up this extra amount of space, so we can't put any electronics in this middle area here. Ideally we want to keep everything in this ring in the middle, but we could spread out the PCB anywhere up to around this area here before it starts hitting places on the microscope, and we could cut out space for these separate LED boards that are going to be mounted at an angle to the main board. So given that each LED driver is going to drive two LED boards, it looks here like it probably makes most sense if we put these drivers somewhere around here. So we're going to position these at the moment just arbitrarily, one each side, because we want to try and keep the distance between the LEDs and these DC to DC converters as close as possible. So next we need to lay out the brightness control, which is most likely going to sit at the front here. So we're going to have the potentiometer and probably the power switch as well. And the power connector itself is more likely to go somewhere towards the rear of the device. So as with the DC to DC converter, we don't need to worry about connecting up all of the nets just yet to external parts like the 24-volt rail and off to the DC to DCs. What we want to do is try and create a nice tight layout of all of these parts. Sometimes it makes sense to try and lay it out similarly to the schematic, because generally speaking, when you're drawing out your schematic, you're drawing it quite logically anyway. So we'll see how that pans out as we start to lay out all of these parts. So there's the layout of this part complete. So that's all of this area just here, pretty much laid out exactly as it is on the schematic, just with a few tweaks. There are still some rat's nest lines, as you can see in green. That's because we haven't placed the power planes yet, so it's indicating that there's a loss of connectivity between a few of those parts. But we can see how that's going to fit on the PCB if we move this up into place and see where we are. So it looks like we can actually have the potentiometer fairly well recessed, although we probably do want it poking out probably around to that point. So we're not going to foul on the center area here. We've got lots of space here. We can now put the power switch in place. So that power switch is SW1, and we'll probably have that just sitting off to the side just next to it. So I've made a few changes. I did print it out and test it against the microscope, but this is absolutely huge. I didn't quite get the sense of scale. So I've reduced the footprint quite a lot of the ring light, and this is much more acceptable. So the area in the yellow part here is the PCB that we're actually making today, and then the LED boards are going to sit out here like this. And we've got the 24 volt supply coming in just at an angle so that it misses the area at the back of the microscope. And then we've got the power and brightness at the front here. So what I'm going to do now is start connecting all of the various bits up together and put in the power planes. So first of all, with the ground plane, we're probably just going to stick with a 0 volt ground plane on both the top and the bottom. Having a look at the circuit, it doesn't really make sense to have, for example, a 24 volt ground plane, because the 24 volts is just going straight down to the switch and then off to the two DC to DC converters. Similarly, the 5 volt rail is only local around here, so probably no reason to have a 5 volt rail either as a plane. So I think we're just going to go with the ground plane top and bottom, which we can create here. We'll pick the ground as the bottom copper, and then also one on the top. Now, because the 24 volt input is a through-hole mounted part, we do actually automatically have connectivity to both layers, but it's worthwhile adding in some vias wherever possible. The DC to DC converter datasheet did suggest having them in these locations here, so we're already tying the two planes together, and that helps decrease the impedance between the two planes, especially where you've got high-speed electronics like this here. Around this area it doesn't matter too much, so we probably will put some vias in after we finish doing all the layout, but now all I need to do is just put some tracers around the PCB to fill in the blanks. Right, so that's all of the connectivity completed. The thing that I like to do next is to turn off all of the layers other than the top and the bottom copper, and just have a look at what the layout actually looks like, and just check that we've got a good path for the ground plane. Now obviously when we route the 24 volt lines and everything, we know exactly where the current's going to go, but what can happen is once you've started routing out all of the lines, you can suddenly chop off part of the ground plane and concentrate the currents down a tiny path, for example. So we just want to check around and make sure that that hasn't happened anywhere. So the areas of interest in particular here are in these two areas where we've got all of these vias which are connecting the two planes together, but these are close to areas where we do need that ground return path. And we can see here we've got a good route all the way up to the 0 volts up here for that. But on this layer you can see on the top copper, we haven't really got a very good route all the way back up to the 0 volts. You can see it's been chopped off by this 24 volt rail that we put on here. So now if we take a look at the bottom copper, you can see also we've blocked off any current paths of any decent magnitude by these lines going across here. So we do want to try and rejig this a little bit. Potentially this 24 volt rail we actually want to take around this way so that we've got a good path to the 0 volts all the way up to the 24 volt connector. So I think we do need to rejig that. We've basically blocked off our current paths, and we're going to end up with very concentrated areas where we see lots of current. So for example, there is a path around here, but we will concentrate the current flow in this area, and if we've got any high frequency stuff, it becomes a easy place for the noise to radiate. So I'm going to reroute this and then have another look. So you can see I've now rerouted this. I've dropped it down to the bottom layer, then brought it back up near the capacitors on the input to the DC to DC. It will add a little bit of impedance and a little bit of inductance with these vias here instead of a straight copper path, but that should be okay. The main thing is now we've got a good path between these nodes here and the 0 volts on the connector. So that's looking good. Next we just need to check the area around here, but I think everything here looks pretty good. So I can't see any particularly congested areas, bearing in mind that all of this stuff is low current now anyway. The higher current parts are already in quite a thick trace, so I think we're looking quite good. I might want to round off some of these corners, so I might revisit the actual board outline just to tidy up some of the areas, but we're pretty much there with this PCB. So I think that's the main PCB pretty much finished. I've just filled the area with some vias here. On the original layout I did have just a few tightly clustered vias like it suggested on the datasheet, but I've got rid of that and just put these vias that are spaced 1mm apart. Now there's way more than we need on here. It really matters around the DC to DC converter because there's some areas here where the current does dip onto the bottom layer and then back up onto the top layer. So that's the reason why we've got the two planes tightly coupled with those vias. But JLC PCB don't really scrutinise you for having lots of vias on the PCB. When it comes to volume production, that will be looked at, and you would either have to pay a penalty in terms of cost, or you would be expected to reduce the number of vias in this type of application, because every hole that you drill, first of all, costs the PCB supplier time, but it also costs them in terms of drill bits, because the FR4 material does wear down those drill bits fairly rapidly. So, you know, when it comes to production, you would want to optimize that. But for this, it's absolutely fine. In the next video, what we're going to do is design those LED boards, and then we will do the pick and place files and the bill of materials files and upload those to the JLC PCB website. So I hope you enjoyed the video. If you've got any comments, again, leave them down below. Any are greatly appreciated. And until next time, thanks for watching.